Hey guys, you are in for a treat today. I don't know if you know this, but I'm actually a pretty famous YouTuber. I have, I think, a whole 100 subscribers. I know, calm down, it's okay. But I did this a lot last year with my pre-algebra and my 7th graders, where we watched a video and then did the work in class. Today we're only doing this because I won't be here for each period. So all of you in each period, hello. It's good to be here with you, even though I'm technically not here. And I just want to make sure we don't get behind. So today we're going to look at graphing step functions. And in case you hadn't guessed from the name, a step function kind of looks like a series of steps. So it is a piecewise function, and it is made up of a series of horizontal line segments. And again, notice that with these segments, a lot of times the next segment will kind of start where the last one picked up. And again, we only have one closed circle on the same vertical line, because otherwise it wouldn't be a function. So this one's open, this one's closed, this one's open, this one's closed. We wouldn't have them both closed. And again, a step function really just is called that because it looks like a series of steps. So with this function, this one would be a piecewise function. It's -3 between -4 and -1 on the x-axis. Then y equals -1 between -1 and 2. Again, notice the less than or equal to for the open circles, the less thans for the open circles, and the less than or equal to for the closed circles. And then it's up here at 5, so y equals 5 for x values between 2 and 4. So again, these functions are just horizontal lines, so you'll see they're just equal to constants. There's no x in the equation there. Now the domain of this function, if you look from left to right, the graph starts at -4 and ends at 4. So the domain is all real numbers x, such that x is between -4 and 4, including both of those because we have a closed circle on both ends. The range, in this case, there's only 3 possible values for y. So the way we would just say that is that y could equal -3, -1, or 3. Those are the only y values that exist in this function. And is this continuous? I think you can see that we can't continue. We can't draw this without lifting a pencil, so this would be discontinuous for this function. Now, we're also going to look at what we call the greatest integer function. So the greatest integer function is a type of step function. And you see these kind of like a double vertical bar, double bracket sort of around that x. So this means the greatest integer less than or equal to x. So for instance, if I have a number in here, so you would put like a number in there. If I see those double bars, this means the greatest integer of 10.7. So the greatest integer less than or equal to this. So what's the closest integer to this, but not bigger than this number? And that would be 10. If we have the number itself, it would just be equal. So if we have -6.35, what's the closest integer to -6? It's not bigger. Be careful with negatives, because technically -6 would be bigger. -7 is less than this value right here. So our output cannot be greater than the input. It could be equal, but it can't be greater. So again, just a couple other examples. If I have, let's say 11.97, we're not rounding it, okay? But we want the greatest integer that's closest. What's the closest integer to this, but not bigger? So 12 is the closest, but the one that's not bigger is 11. Okay, so that's what that greatest integer function looks like. And the series, and that function is kind of a series of steps. So if you think about it, any number between -1 and 0, what's the closest integer to that? Well, if I have -0.5, and then the closest integer that's not bigger is -1. So all these values are -1. If I have, let's see, this is 1, 2, so 2, let's say right here. If I have on the x-axis 2.8. Let's just say we go to 2.8 on the x-axis. What's the closest integer to 2.8 that's not bigger than that? And that would be 2. So any value between 2 and 3, the closest integer not bigger than that would be 2. Does that make sense? So you would graph each of these as a series of steps. So we're going to look at graphing a step function. And again, if you have all the pieces, you're really just graphing a set of horizontal lines. So there's going to be some where you have the pieces and you just have to graph them. But some of these you'll have to actually figure out what that step function is. And a lot of these are situations like this, where if you look here, the cost of mailing a first-class letter is determined by rates adopted by the U.S. Postal Service. The rates adopted in 2016 charge 47 cents for letters not over 1 ounce, 68 if not over 2 ounces, 89 if not over 3, and 110 if not over 3.54. So if you think about it, this is a series of steps, right? 1 ounce or less costs 47. Between 1 and 2 ounces, it's 68 cents. Between 3 and 3.54, or between 2 and 3, it's 0.89, and between 3 and 3.54, it's 110. So the first thing we're going to do is kind of make a table with these values. So if x is between 0 and 1, then the cost is 47 cents. If x is between 1 and 2, then the cost is 68. 2 and 3, cost is 89. 3 and 3.54, the cost is 110. Notice that if it is equal to 1 ounce, it would be 47 cents. If it's equal to 2, it's 68. So not over 2 means less than or equal to 2. Not over 3 would be less than or equal to 3. So our equal to goes with this side of our value. And so here basically is what we have as our step function. And now that we have that, we're going to make a graph of this. So this would be like our function, our piecewise function. And so if we're going to graph this from 0 to 1 ounce, it costs 47 cents. Then from 1 to 2 ounces, it costs 68 cents. From 2 to 3, it costs, what did we say, 89 cents. And then from 3 to 4, it's $1.10. So again, you just have 4 segments representing the 4 different tiers of costs. And so the domain of this function, if you look from left to right, we start all the way at 0 and go all the way to what, 3.54 for our x values here. And then the y values, if you look, y can only equal those costs. So my range is just those 4 values right there. If we are graphing a greatest integer function, so look at this next example, and you guys could be following along in your books, but if I want to graph the greatest integer of 2x minus 1, again, what we're going to do is actually make kind of a table of values. So in this case, these intervals were chosen because we have this 2 here. So the reason we choose intervals of a half is because if I put like negative 0.5 in here, so if I'm going to take negative 0.5 and plug it in, negative 0.5 is negative 1/2. So if I plug in negative 1/2, 2 times negative 1/2, that helps us not have any more fractions to deal with, and we're not dealing with decimal values for our y. So that's why you see that these intervals involve halves. 2 times negative 1/2 is negative 1. Technically, 2 times negative 1/2 is negative 1 minus 1 is negative 2. So this is the endpoint. So negative 2, when it's equal to negative 1/2, like here, our integer will be negative 2, but this one's not equal to. So this one is the negative 3. And then this is going to be negative 1, anything between 0 and 0.5. So let's just say I plug in 0.5 here, then that's going to equal 1, but this is a less than or equal to. So I don't want, oops, I didn't want that to go away. But these are going to be -2. I guess I could just type it here instead of writing it. Let's go -2. Because again, if I plug in -1/2, that's equal to -2. And so this is the step, if you will, where we can have the equal to. If I plug in 1/2, this equals 1, or 0, I should say. If I plug in 0, then this is going to equal -1. 2 times 0 is -1. And then if I plug in 1, so this is what we can do. We can plug in the equal to side, and that'll help us figure out, oops, which one we have here. So if I plug in 1.5, 2 times 3/2 is 3, 3 minus 1 is 2, and so we'll plug in the value of the equal to side for our function here. That'll make more sense. And then again, it's just a step function. So these are all going to be horizontal line segments. Okay, and so our first one is from -1 to -1/2. So from -1 to -1/2, we have a horizontal line segment at -3. And then our next ones, if we want to just keep going, once you have the pattern, you can kind of just fill in. So once we have a few, you can kind of see what's going on. And you don't, technically these steps would keep going and going. So this would keep going, but you don't have to draw the entire thing. Now let's think about domain and range for this function. Like I said, these steps, if you look at the function, x can be any value. We just picked a few values for x to make our graph, but if you think about it, x could actually be any real number. So the range is all, the domain is all real numbers. We could put any number in for x, but if you look at what comes out, does y go? Technically, yes, y keeps going up and up and up and up. This is going to keep going. But is every y value represented? And the answer is no. There's no y values here or here or here. So the range in this case is only integer values because it's called the greatest integer function. Any number can go in for x, but the only things that come out are integers. So the range, we would just say, is all integers. Now, the other types of graphs you're going to have to know are absolute value graphs. An absolute value function, you guys know what absolute value means, and you know what it looks like. So absolute value of x looks like this. Again, you can almost define it and graph it as a piecewise function, but we're going to be looking more at these in the next section as well. The absolute value function is what we call a parent function, which is the simplest of the functions in a family. So the next section, we're going to be looking at function families, but we're going to look at a quick introduction to absolute value functions right now. So with absolute value functions, first of all, the absolute value of a number we know is always positive, which is why the graph looks like this. If you remove the bars, f of x equals x is really just this line through the origin, right? So if we remove the absolute value bars, then this part just kind of becomes a line. But when we put in those absolute value bars, then our graph is always positive. So instead of this line continuing, we've taken this negative part and kind of flipped it up here. Okay. Again, you could think of this as a piecewise function. It's going to be x if x is greater than or equal to 0. So the slope is positive. Then it's going to be negative x, or the opposite of x, when x is less than 0. So it's the same line, but the slope is negative in this case. So it's kind of like a piecewise function here. The domain is all real numbers, but the range is only positive values of x, so 0 or greater than 0. And again, in what is it called? Set interval notation, set notation. We remember we have the curly brackets f of x such that f of x is greater than or equal to 0. Let's see if I can get this back here. And y, there we go. Okay, and in this case, it has just one intercept for x and 1 for y, and it happens to be the same point, so 0, 0 is our intercept. So if we want to graph absolute value functions and we have a positive coefficient, again, we're just going to, you could almost graph this part like you were graphing a line 3/4 x plus 3. So we could make a table. We can pick some values of x and f of x, probably some negative and some positive, and plug them in. So again, one way to graph anything is to always make a table of values, and then graph all those points, and we should see that V shape right there. But another way to do this, well, first of all, domain and range. So domain is all real numbers, and in this case, we notice that this is the lowest point. So f of x or y is greater than or equal to 3. Where's our other method? Do they show us here? Our other method is to treat this as a series of lines. So if I were to graph the line y equals 3/4 x plus 3, if you see that 3/4 x plus 3, I start at 3, I go up 3 over 4 to make my new line, and then I can make that line here. But it's only going to be this when x is greater than or equal to 0, right? And then when it's less, what we're essentially doing again is taking this left half of the graph and flipping it up. So what happens? Does the y-intercept change when we do that? No. But what happens? It's the same slope, but now it's up 3, left 4. So now, for the first part of the graph, it's 3/4 x plus 3. But the second half is negative 3/4 x plus 3. So when x is greater than or equal to, I don't know why this does this, greater than or equal to 0. And when it's less than 0, it's this left part. So let's see if I can get this to zoom without disappearing. There we go. So I would still go up to 3, but instead of going down 3, 4 right, I can go up 3, 4 left, and then create the graph that way. So again, it's just really those two lines, one with a positive slope, one with a negative slope there. Okay. So that's another way you can graph that. We're going to look at other ways in the next section as well. Now, if it has a negative coefficient, and I don't like my videos always being this long, but today it is what it is. We've got a lot to get through. So with a negative coefficient here, probably we can do this with two cases. So we can do this making a table, or we can think about the fact that this function really has two different cases. First of all, if what is in the absolute value, if the input for x is positive, okay, then the absolute value is going to be x plus 1. And if I simplify this, then I get negative 2x minus 2. But if x plus 1 is negative, so if x plus 1 is positive, if this is a positive number, then what comes out is just that number itself, x plus 1, right? But if x plus 1 is a negative number, so inside the absolute value, if I have negative 3 in there, then what comes out is the opposite of that, positive 3. So if this is negative, okay, if x plus 1 is negative, then what comes out is the opposite of x plus 1, the whole quantity x plus 1. So I would multiply this negative 2 times the opposite of x plus 1, which if I distribute that negative 1, that's where this is, and simplify that, then these are my two cases here. So in this case, this is 2x plus 2 if x is less than negative 1, negative 2x plus 2 if x is greater than or equal to 1. And if this doesn't make sense, go back and rewind it and watch this again for domain and range, because I don't want to make this too long, and we are going to spend some more time on these in class. So look through this example again, see if this makes sense. Pause here, take some time to read through this. And then what we have again is just two lines. So we're graphing those two lines, but we're cutting them off at 1 and -1. Why -1 in this case? Well, because -1 plus 1 is 0. Okay, so that's where our graph actually starts, is on this axis here. Again, we're going to talk more about this, but at least see if you can see where these two pieces come from. And if it doesn't make total sense for this one, that's okay. But you should be okay with the rest of these absolute value and step functions, hopefully. And we will spend time in class tomorrow going over all the homework. So do your best and work together on the homework today in class. Those of you in H period, help each other out, but we will go over this in class tomorrow. All right, have a great rest of your day, guys.